Today we'll look at a problem that is a little bit more complex than it looks. So we have a 20 centimeter long spring with a spring constant of 1200 newtons per meter set vertically on the surface. So that's our spring here. The spring is 20 centimeter long, so 20 centimeter above the surface. A 800 gram block is dropped 50 centimeter above the surface. So it's dropped from rest in here. And the question is, what will be the length of the spring once it reaches its maximum compression? So essentially at the moment the spring will be at its shortest length. So I already prepared a solution to this problem, but in the solution there is an error. So what I want you to do is to pause the video and to tell me where the error is. Do you think the error is in part A, the error is in part B, C, or D? Alright, so I'll let you think about it a little while. Alright, I hope you found the mistake. It's classic to think that the mistake will be the math, but often in physics the worst mistakes are the ones that are happening at the beginning, and they are unfortunately the most common as well. Here, right at the beginning, when we're assuming what's the final height of the block, we're making a big mistake, because in the end, the block will be squishing the spring. So the spring will actually be a little bit shorter and the block will sit on top. So the final height of the block will not be the 20 centimeter, but will be a little bit lower than that. And we had not account for this. In other words, when we assume in here that the potential energy at the end is for a height of 200 meters, we're actually overestimating that height a little bit, and that's what we need to fix. Sadly, this small change actually creates a big difference in the solution, and it will make things a little bit more complex, and that's what we'll be looking at next. Alright, so let's solve this problem correctly. So we know that we have the 20 centimeter long spring, we know that the spring constant is 1200 newtons per meters, the mass of the block is given, we know the initial height of the block as well. And what we're looking for is the length of the spring once it reaches maximum compression. The maximum compression is actually a very important piece of information. So now that we have all of this, I restarted the problem in exactly the same way as before. We want to collect the information, which we kind of did here. Because we know there's a spring in there, really our best shot is to use conservation of energy. So we'll need to account for the kinetic energy, the potential energy due to gravity, as well as the potential energy of the spring, the elastic potential energy, so EL. I decided at first, in the first problem, to choose the height to be 0 on the ground. This is a valid choice, but it's not necessarily the best. So what I want to do in here is to take a different choice for that. And the choice I want to make is to actually take my H will be equal to 0 at the initial length of the spring. This will simplify the algebra later down the road. So in here, the H is equal to 0 will be reset slightly differently. And because of this, we need to adjust what will be the initial height. Instead of having the 50 centimeter above, now we only have 30 centimeter above, so 0.300 meters. So after that, we can figure out what will be this height of the block at the end, and that's really where we messed up in the first problem. So the new final height will be looking something like this. But since our 0 is in here now, the height that we're looking for is actually this height in here. So the value that we'll get in here is HF. That's actually an unknown. But what we see is that it will be the same as the compression of the spring. So although these two quantities seem to be two different unknowns, they are actually linked together. And that will save us and allow us to solve for the problem. So energy bar chart, always a good idea. So what type of energy are we dealing with? At the beginning, there is no kinetic energy. We have some potential energy due to gravity. We have no compression in the spring initially, so the spring energy is equal to 0. And in here, there's no friction, no external force that is doing work, so we don't have to worry about this one. At the end, the kinetic energy will also be 0. And we know this because we know it's at max compression. So if it's at max compression, this means that it's about to change direction, and therefore the kinetic energy and the speed will be 0. The potential energy due to gravity, because we're lower than our h equals to 0, we know that this quantity will actually be negative. And therefore, this means that the potential energy stored in the spring will actually be greater than what we had in terms of potential energy at the beginning, because the two of these together needs to add up to the same amount as the potential energy due to gravity initially. So we can now try to solve the problem. So we know that we will have the mechanical energy at the beginning plus the work done by any external force is equal to the mechanical energy at the end, which is essentially what the energy bar chart is saying. So if you want to be thorough, kinetic energy plus potential energy due to gravity plus potential energy of the spring initially plus the work done by external forces will be equal to the sum of the final kinetic energy plus final gravitational potential energy plus final potential energy of the spring. However, as is often the case, a lot of these turn out to be zero, so we don't have to worry about them. And that will simplify greatly our calculations afterwards. So what's left in the end will just be the mass times the acceleration due to gravity times the initial height, which is the gravitational potential energy at the beginning. We have the same expression, but for the final height, which will give us the final potential energy due to gravity. And we also need to add the potential energy due to the spring, so 1/2 times the spring constant k times x final squared. And all of these numbers we know with the exception of h final and x final, but h final we just found was the same in length as x final. So essentially we have a single unknown in here, and now we just have to plug in the number and solve that equation. So we will restart from this equation, and you can see that we have one term without the unknown, one term linear in the unknown, and one term with the square. So you should realize that we will need to use the quadratic equation to solve for this. So I'll just rewrite my equation slightly differently. I will have the 1/2 k x final squared on this side plus the mg x final. And then I will bring this one on the other side so that we have minus mass times g times h initial. And we know that all of this will be equal to 0. At this stage, I will plug in the numbers to simplify the equation a little bit. So we will have 1/2 times 1200 newtons per meters times x squared. So we will have our unknown in here, xf squared, plus the mass, which is 0.800 kilograms, times g, 9.80 meters per second squared, times xf, and then again minus the mass, so 0.800 kilograms times 9.80 meters per second squared times the h initial. And the h initial, if you remember, our h0 is here, so this was just 30 centimeters, so 0.300 meters. Once simplified, we get 600 xf squared plus 7.84 x final minus 2.352, and all of that is equal to 0. So then in order to find the value of xf, you want to use the quadratic equation. So this will be the minus b plus or minus square root of b squared minus 4ac, all of that divided by 2a, where the a will be equal to 600. The b will be just the value here, so the 7.84, and the c is the minus 2.352. We can now calculate the roots, and I'll spare you the details. I know you can do this. The two roots that we will find for the value of xf are xf is either equal to plus 0.0564 meters, or it's equal to minus 0.0695 meters. So we have to decide between the positive root and the negative root. And it's not necessarily obvious which one you should choose. So to figure it out, there's two ways you can see it. In here, I think the easiest is to realize that the value we expect to have for HF, because we know that there's a negative amount of potential energy due to gravity at the end, because of our choice of h is equal to 0, tells us that hf should be negative. And since we know that hf is equal to xf, and we have that hf should be a negative number, then we know that we have to choose the negative root. So this means that our value would just be that xf is equal to minus 0.0695 meters. The positive root would be used if, for instance, you imagine that this block would be glued to the spring. So after it compresses the spring, it would move up, and on the way up, eventually it would stop because the block is now glued to the spring. The maximum height it would go back on the way up would be the other root that we're finding here. The question was actually asking for the length of the spring at the end, so we have one more step to do. L final will be equal to 20 centimeters plus the compression of the spring. The compression of the spring, we have to transform it in centimeter as well, so it will be plus minus 6.95 centimeters. And once we finish the calculations, we'll get that the length of the spring is equal to roughly 13.05 centimeters. So final length is equal to, once we round it, 13.1 centimeters. So this is the answer that we're looking for, and that's basically how we solve the problem. Thanks.